Okay, so we are starting definite integration today. Okay, so previously we have, let's write the date. So today is 3/23/20. It's not actually that, it's the 19th right now, but it will be for you guys. So far you guys have done integrals where you integrate something and it doesn't have any value in these spots right here. Okay, so those spots are where we're going to start adding values with definite integration. So first we're going to talk through a little bit of the conceptual understanding of definite integration. Sorry for all the blurry zooming in and out. Okay, so integration is being used in this case to find a specific area under a curve. Okay, so we have a curve right here. I'm gonna color it in red. Okay, and we're making an effort to approximate what it is. And so what we do is we take these rectangles, so these guys right here, okay, and we're going to have the rectangles have a height of f of x and a width of change in x. The little delta or triangle means change. Okay, so do you guys see how each rectangle goes up and meets the curve on the left-hand corner? And that's how we get the height. So for this particular x value, we map up to the f of x value, and then we make our little rectangle that length, and then we do the same thing for the next one. So clearly this is a bad approximation because we have like this stuff that's over and then we have these white gaps right here. But obviously we're going to make this a very precise and exact calculation. And again, each of these points right here are going to be the point x, comma, f of x. Okay. Okay, so this area under a curve is an approximation. If I can spell approximation. Okay. And it's going to be the sum of our height, our little heights, times each of our widths. Okay, which looks like when we actually write it out with a formula, our f of x's times our change in x's. Okay, and notice right here, I'm gonna highlight that this change in x is corresponding to like how wide each of our little boxes is. Okay, that's what it's talking about. Okay, so this is an approximation, but we're looking for our exact I guess a formula for the exact area underneath the curve. And this formula is going to use our integral of f of x dx. Okay, this dx corresponds to our change in x. And obviously the f of x is the same. Okay, and let's see, this basically this is this as this piece as we take the limit of this piece approaching 0. So we're getting our rectangles like infinitely, like what's the word? Our width is like infinitely small. Okay, so our major concept here is that we're taking the area under our curve from, sorry, my dog is coming in and wanting attention. We're taking our curve f of x and we're mapping two x values down, a to b. These will be our little limits that go here and here. And we're trying to find the area between those points underneath that curve. Okay, so our area is going to be equal to the integral from a to b of f of x dx. This is our lower / smaller boundary. and this is our upper boundary or bigger boundary. Okay, so when we evaluate definite integrals, we're going to actually take the integral just like normal. And do you guys remember that we said like that f, big F of x is going to be, well, I guess this isn't true, but like big F of x is going to be equal to our integral. So we notate that by using the big F here. And instead of getting a function this time, we're going to come up with an actual number. So this is going to be big F of b. So this will be a constant right here. And then big F of a, that will be another constant. And then we'll get a constant value for our area right there. Okay, so let's do an example. Maybe this will make more sense. Okay, so first, let's look at this one. Okay, when we just integrate this like normal with an indefinite integral, what we're gonna get is x to the fourth plus x squared plus c, right? Okay, that's what we would get with an indefinite integral. But this time, we draw this little bar, and we're evaluating this function from 2 to 5, okay? Where 5 is our upper boundary, 2 is our lower boundary. So now we're going to do what we said we would do up here, okay? B is our upper boundary, and we're going to calculate that first. So this is going to be equal to, when we sub 5 into this function, so 5 to the fourth plus 5 squared plus c. And then we want to subtract off our integral evaluated with our lower boundary. So I'm going to have 2 to the fourth plus 2 squared plus c. Now notice, and this is going to happen every single time, that our c's, because there's a minus sign here, are going to cancel out. Okay, we always add c when we integrate. And so we're always going to have a positive c here, and we'll always end up with a negative c here. So your c is just going to disappear, which is super cool. So if we actually calculate this out, 5 to the fourth is 625. Then I'm going to add on 5 squared, which is 25, plus c. And then I'm going to subtract 2 to the fourth, which is 16, plus 4, plus c. So when we, sorry, when we simplify this, I'll get 650 right here, plus c, minus 16 plus 4 is 20. And then I'm going to go ahead and distribute this negative sign to both of these pieces, minus c. Okay, so now here is where my c is going to cancel out in each term. And I'll have 625 minus 20, or I'm sorry, 650 minus 20, which is 630. Okay, so that is our first example. I will do the next example with you as well. Okay, so this is going to be the same thing. I'm going to rewrite the inside of this integral, the integrand, so that it's a little easier to integrate. So I'm going to have x minus 3 times x to the negative 1/2 power dx. Okay. So now this, when I integrate for real, I have x squared over 2 minus 3 x to the 1/2, because I added 1 to this power right here, the negative x, or negative 1/2. Negative 1/2 plus 1 is positive 1/2. And then I'm going to divide that by my new power, which was 1/2. And then I'll have plus c. And don't forget that you have to write, because this is a definite integral, you have to write this little bar with our limits of integration from 1 to 4. Okay. Okay, so now we've integrated. And now let's go ahead and simplify. Okay. So I'll have x squared over 2. Oh man, people are sending me lots of messages right now. Minus 6x to the 1/2 plus c. Claire, we did some fraction stuff here. When we divide by a fraction, we do the thing where we take the denominator and we're just flipping it. So this is really 3 times 2 over 1. And 3 times 2 is 6. Divide that by 1, you still get 6. So that's where the 6 came from. So then, if we were in class, I would have asked you to do it. So then, let's see. First, we want to evaluate with the upper limit. So I'm going to have 4 squared over 2 minus 6 times 4 to the 1/2 power plus c. Then I'm going to subtract off, the lower bound was 1. So I'm going to have 1 squared over 2 minus 6 times 1 to the 1/2 power plus c. Okay. Oh. And then when I simplify this, sorry, this is getting a little stuck. I'm going to have 16 over 2. 4 to the 1/2 power is 2, so this is really going to be minus 12 plus c. And then I'm subtracting off. This is going to be 1/2 minus 6 plus c. Oh, it's getting squished. Sorry, guys. And then when we simplify that even more, I should get 8 minus 12. 8 minus 12 is negative 4 plus c. And then minus, so negative 6 plus 1/2 is going to give me negative 5.5. And I'm subtracting c. And now my c's can cancel. Negative 4 minus 5.5 should give me, did I do this right? No, because inside of here, we should have negative 5.5, and then there's a negative right here, so this should be plus. So negative 4 plus 5.5 should give me 1.5. Okay, so this is my solution for example 2. Okay, so what I want you guys to do is pause the video, and I want you to do 3 and 4 as a you-do and attempt it. I'm going to go ahead and pause this video and start a new one so that this isn't super long and it's not difficult to look at. So go ahead and try these, and then we'll start the next video back up with these 2 you-dos right here. Okay, thanks guys.